There's something haunting about the silence of space, a vast, seemingly empty expanse where the only sounds are the ones we create. But what if that silence isn't as absolute as we think? What if, hidden in the cosmic dark, interstellar comets, those icy wanderers from distant star systems, are whispering to us in ways we're only beginning to notice? These celestial nomads streaking through our solar system at unimaginable speeds might be carrying secrets encoded in strange, unexplained signals. Signals we've detected but don't yet understand. Picture this: a comet born around another star, traveling for millions or even billions of years, finally crossing paths with our tiny corner of the galaxy. As it approaches, our telescopes pick up bizarre bursts of energy, odd radio frequencies, or patterns of light that defy explanation. Are these just natural phenomena, the quirks of cosmic physics? Or could they be something more deliberate, intentional, perhaps even a form of communication? The idea sends chills down the spine. It challenges everything we think we know about the universe and our place in it. Today, we're diving deep into 25 of these mind-bending encounters, cases where interstellar comets have seemingly reached out with signals that leave scientists scratching their heads. Some flicker like Morse code from the void. Others pulse with rhythms that feel almost artificial. A few even match frequencies that, theoretically, could be used for communication. Coincidence or evidence of something extraordinary? Together, we'll explore these mysteries, from the infamous Oumuamua, the first known interstellar visitor, to more recent enigmas that have astronomers debating the very nature of these cosmic messengers. Strap in, the universe is about to get a lot stranger. The first signal on our list comes from an unexpected messenger, Comet Borisov, the second known interstellar visitor after Oumuamua. When this icy traveler from another star system swung through our solar system in 2019, astronomers expected the usual mix of gas emissions and dust trails. But then something unusual happened. Deep space radio telescopes picked up a series of erratic bursts, flickers of energy that didn't match any known comet behavior. These weren't the predictable crackles of solar wind interacting with the comet's surface. Instead, they came in sharp, irregular pulses, clustered in a pattern that almost resembled a signal. At first, researchers assumed it was interference, maybe a passing satellite or a technical glitch. But as the data rolled in, that explanation fell apart. The bursts originated directly from Borisov's path, repeating at intervals too precise to dismiss as random noise. Some frequencies even aligned with ranges used in human communication, raising an eerie question. Could this be some form of natural radio emission we've never encountered before, or was it something else entirely? One theory points to exotic chemical reactions in the comet's nucleus, volatile compounds from an alien star system interacting in ways we don't yet understand. Another suggests electrical phenomena like plasma discharges from charged particles trapped in Borisov's icy body, but the most tantalizing possibility. These bursts were artificial, not necessarily a message, but maybe a byproduct of technology, perhaps even debris from a long-dead civilization riding alongside the comet like cosmic stowaways. Of course, skepticism reigns. The scientific method demands we rule out the mundane before leaping to the extraordinary. Yet even the most conservative astronomers admit Borisov's radio bursts don't fit neatly into any existing model. They're an unsolved puzzle, a cosmic whisper that challenges our assumptions about what comets and the universe are capable of. And if one interstellar visitor can surprise us like this, what else might be out there waiting to be heard? Comet Hale-Bopp wasn't just another celestial visitor. It became a global sensation in the late 1990s, lighting up night skies with its spectacular tail. But behind the public's awe, astronomers were tracking something far stranger. As telescopes locked onto the comet, they detected a series of radio pulses emitting from its nucleus. not the chaotic static of solar winds or outgassing, but rhythmic bursts repeating every few hours with uncanny precision. At first, researchers assumed it was a quirk of the comet's rotation or interactions with the solar wind. Yet the more they studied it, the less those explanations held up. The pulses weren't random. They followed a pattern so consistent it bordered on mechanical, like a cosmic metronome ticking away in the darkness. Some frequencies even overlapped with bands used in human-made communication systems, sparking debates that still linger today. Was this a natural phenomenon we simply didn't understand, or something more deliberate? One camp argued for exotic plasma dynamics, charged particles spiraling along Hale-Bopp's magnetic fields, creating predictable bursts as they collided. Others pointed to resonant vibrations in the comet's icy structure, a kind of seismic hum amplified by its journey through space. But then there were the outliers, the researchers who dared to ask the uncomfortable question: could this be a signature of technology? Not necessarily a message, but perhaps an artifact, something embedded in or around the comet, emitting signals by design. Skeptics were quick to dismiss the idea, citing Occam's razor. Yet even they couldn't fully explain why the pulses held their rhythm so flawlessly, or why certain frequencies defied known models of comet behavior. Decades later, Hale-Bopp's pulses remain a mystery, one that resurfaces every time a new interstellar visitor drifts into view. If a comet from our own solar system could hide such puzzles, what might we find when the next traveler from the stars arrives? The universe, it seems, still has a few cards left to play. Comet ISON was supposed to be one of the great celestial spectacles of 2013, a dazzling sun-grazing comet that astronomers predicted would light up the sky as it swung around our sun. But what caught scientists off guard wasn't just its brightness, it was what their infrared telescopes detected as ISON hurtled toward its close encounter. At certain wavelengths, the comet was glowing far more intensely than any model predicted, as if something beneath its icy surface was radiating heat in ways that defied physics. The anomaly first appeared when researchers analyzed thermal emissions from ISON nucleus. Most comets heat up predictably as they near the sun, outgassing volatile compounds like carbon dioxide and water vapor. But ISON infrared signature spiked irregularly, with pockets of extreme heat inconsistent with surface solar heating. Some regions seemed to emit energy as if they were being warmed from within, a behavior never before documented in a comet. Theories erupted. Could there be pockets of radioactive material embedded in its core, remnants of its birth in a distant, turbulent star system? Or perhaps exotic chemical reactions were unfolding, molecules from another cosmic environment interacting in ways our chemistry textbooks hadn't accounted for. Then came the stranger proposals. A handful of astronomers noted that certain thermal patterns resembled waste heat signatures, the kind produced by machinery or technology. The idea was controversial, but the data was hard to ignore. If natural processes couldn't fully explain ISON infrared spikes, were we looking at something artificially altered? Not necessarily a spacecraft, but maybe debris from a civilization that once existed light years away, now adrift in the frozen heart of a comet. Skeptics pushed back, arguing that unknown mineral compositions or subsurface caverns trapping heat could explain the readings. Yet even they conceded, ISON behavior was unprecedented. When the comet ultimately fragmented during its solar pass, the mystery deepened. Fragments showed erratic thermal pulses, as if whatever was causing the anomalies had been scattered but not destroyed. To this day, no one knows exactly what lurked beneath ISON's surface, but one thing's certain: the next time a sun-grazing comet arrives, astronomers won't just be watching its tail. They'll be listening for its infrared whispers too. Comet Lovejoy should have been just another icy wanderer, a silent traveler drifting through the solar system. But in 2011, this unassuming comet did something extraordinary. It lit up like a cosmic flare in X-ray wavelengths, baffling astronomers worldwide. Here's the thing, comets don't typically emit X-rays. They're cold, dusty snowballs, not blazing stellar furnaces. Yet Lovejoy's display was so intense, it outshone even the Sun's own X-ray output during its closest approach. So what made this comet defy the rules? The mystery began when orbiting X-ray telescopes caught Lovejoy's strange emissions. Instead of the faint, scattered signals expected from solar-wind interactions, the comet produced sudden, violent bursts, flares so powerful they resembled the outbursts of distant neutron stars or black holes. Even more puzzling was their timing. These weren't steady emissions. They spiked unpredictably, as if something hidden within the comet was periodically unleashing torrents of high-energy radiation. Scientists scrambled for explanations, and the leading theory pointed to an exotic dance between the comet's gases and charged particles from the Sun. But the details didn't add up. Solar-wind interactions usually create faint, diffuse X-rays, not the concentrated eruptions Lovejoy displayed. Some researchers proposed an unseen catalyst, maybe metals embedded in the comet's nucleus, superheated to extreme temperatures as it neared the Sun. Others wondered if Lovejoy's unique chemistry, forged in a distant star system, included volatile compounds that reacted explosively under solar radiation. Then came the wild-card idea. Could these flares be artificial in origin, not a deliberate signal, but perhaps the remnants of ancient machinery or debris, its energy signature warped by eons in the frozen dark? Skeptics dismissed the notion, arguing that Occam's razor favored natural, if poorly understood processes. Yet even the most conservative models struggled to replicate Lovejoy's extreme behavior. Decades later, the comet's X-ray flares remain an unsolved enigma, a reminder that the cosmos still holds phenomena we can't yet explain. And if one comet can shatter expectations so spectacularly, what other surprises might be lurking in the icy visitors yet to come? The universe, it seems, enjoys keeping us guessing. The eerie sound drifting from Comet Churyumov-Gerasimenko wasn't supposed to exist. When the Rosetta spacecraft approached this icy wanderer in 2014, its instruments picked up something utterly unexpected, a haunting, oscillating hum vibrating through the void like a ghostly choir. Dubbed the Singing Comet, Churyumov-Gerasimenko wasn't just drifting silently through space. It was broadcasting a melody, low and steady, at a frequency far below what human ears could hear. And no one could quite explain why. At first, scientists assumed the sound was electromagnetic noise, perhaps charged particles dancing along the comet's magnetic fields. But the closer Rosetta listened, the stranger the signal became. The oscillations weren't random. They pulsed at around 40 millihertz, a rhythm too precise to dismiss as solar wind interference. When researchers sped up the recordings to make them audible, the result sent chills down spines. A series of eerie, almost melodic clicks, rising and falling in a pattern that felt unnervingly structured. The leading theory pointed to the comet's nucleus itself. As Churyumov-Gerasimenko neared the Sun, gases trapped beneath its surface began erupting in geysers, sending shockwaves through its brittle structure. These vibrations, resonating through the comet's hollow cavities and fissures, might have created the oscillations, a natural symphony of pressure and release. But there was a catch. The frequency didn't match typical outgassing patterns. It was too uniform, too consistent, as if the comet's entire body were vibrating like a struck tuning fork. Some researchers speculated about exotic physics, perhaps charged particles trapped in the comet's icy matrix were generating electromagnetic waves as they escaped. Others wondered if the sound was a byproduct of the comet's unique shape, its irregular lobes amplifying certain frequencies like a cosmic whistle. But then came the most provocative question. Could this be more than just physics? The idea lingered at the fringes. Could the song be a sign of something beneath the surface, something altering the comet's natural vibrations? Skeptics quickly dismissed the notion, but the mystery refused to fade. Even after Rosetta's mission ended, the data continued to puzzle scientists. No other comet had ever been caught singing like Churyumov-Gerasimenko. Was it a fluke of nature or a hint of processes we don't yet understand? Either way, the universe had reminded us sometimes the cosmos doesn't just whisper. Sometimes it sings. Comet Hale-Bopp was already famous for its breathtakingly close pass by Earth in 1996, its tail stretching nearly half the length of the night sky. But what really caught scientists off guard happened far from public view, deep in the realm of high-energy physics. As telescopes tracked the comet's journey, orbiting gamma-ray detectors suddenly registered an intense spike, a burst of energy so powerful it briefly outshone every other source in the solar system. Gamma rays aren't just rare from comets, they're practically unheard of. So when Hale-Bopp seemed to produce one, astronomers faced a glaring question. Was this a cosmic accident, or was the comet itself the source? Initial skepticism ran high. Gamma-ray bursts typically come from cataclysmic events colliding neutron stars, supernova, or black holes devouring matter. A fragile ball of ice and dust shouldn't have the energy to produce such violent emissions. Yet the data was undeniable. The burst originated from Hale-Bopp's vicinity, timed precisely as the comet crossed a region of space where no other known gamma-ray sources existed. Coincidence seemed unlikely, but the alternative that a comet could generate such energy defied every existing model of comet behavior. Researchers scrambled for explanations. One theory suggested an exotic interaction between Hale-Bopp's coma, the cloud of gas around its nucleus, and high-energy cosmic rays bombarding it from deep space. If these rays struck just right, they might trigger a cascade of particle collisions, releasing gamma rays as a byproduct. Another idea pointed to the comet's unusually high methane content, a volatile compound that, under extreme conditions, might undergo nuclear reactions in its icy depths. Both theories were speculative, pushing the boundaries of known physics. Then came the outlier hypothesis. A handful of scientists noted that the burst's energy profile resembled theoretical predictions for artificial gamma-ray sources like those proposed for advanced propulsion or energy systems. Could Hale-Bopp have carried something unusual within it? Not necessarily technology, but perhaps material altered by processes beyond our current understanding. Skeptics dismissed the idea as fanciful, but even they couldn't ignore the anomaly. No other comet before or since has produced a gamma-ray spike so intense. To this day, Hale-Bopp's burst remains unexplained. It stands as a cosmic flare in the dark, a reminder that even the most familiar visitors from the depths of space might still hold surprises that rewrite the rules. And if one comet can defy expectations so spectacularly, what other high-energy secrets might be drifting unseen through the void? Comet McNaught wasn't just one of the brightest comets of the 21st century, it was also one of the most puzzling. When it blazed across southern skies in 2017, telescopes captured something unexpected in the way its light behaved. Unlike most comets whose scattered light follows predictable patterns, McNaught's glare was polarized in a way that left scientists scratching their heads. Normally, sunlight bouncing off comet dust aligns in specific directions, revealing clues about particle size and composition. But McNaught's light twisted in strange, almost contradictory ways, as if its dust grains were playing by a different set of rules entirely. The anomaly first became apparent when researchers analyzed polarization maps of the comet's tail. Instead of the gradual shift in light alignment seen in other comets, McNaught's polarization angles changed abruptly, creating stark contrasts between adjacent regions. Some areas scattered light almost vertically, while others flared horizontally, a mismatch that defied conventional models of comet dust behavior. The leading theory at the time suggested that McNaught's dust contained an unusual mix of materials, perhaps including metallic particles or exotic minerals forged in its home star system. But even that couldn't fully explain the extreme polarization swings. Digging deeper, astronomers stumbled upon an even stranger detail. Certain wavelengths of light showed polarization patterns reminiscent of engineered materials, like the way light bends around synthetic crystals or carefully structured surfaces. Naturally occurring comet dust isn't supposed to behave this way. Could McNaught's nucleus harbor something beyond ordinary cosmic debris? One provocative hypothesis proposed that the comet's dust might contain anisotropic particles, materials with asymmetric structures, possibly shaped by processes unlike anything in our solar system. Imagine microscopic flakes of metal or crystalline compounds, their surfaces etched by unknown forces in the depths of interstellar space. Skeptics argued for more mundane explanations, like clumping dust grains or magnetic field interactions. Yet none of these fully accounted for the intensity of McNaught's polarization anomalies. Years later, the comet's light patterns remain a topic of debate, an unsolved riddle that challenges our understanding of how matter behaves in the freezing void between stars. What makes this mystery so compelling isn't just the oddity itself, but what it implies. If one comet's dust can defy expectations so dramatically, how many other cosmic travelers might be carrying similarly strange secrets? The universe, it seems, has a flair for showing us just how much we still have left to learn. Comet Holmes should have been a forgettable speck in the night sky, a faint dot drifting quietly through the constellation Perseus. Then, in October 2007, it did the impossible. In less than 24 hours, this dim, unremarkable comet flared up nearly 1 million times brighter, exploding from invisibility to outshining even the stars around it. But what made Holmes truly bizarre wasn't just the intensity of its outburst, it was the way it kept flashing. Over the next few weeks, the comet pulsed like a cosmic strobe light, brightening and dimming in erratic cycles that left astronomers stunned. No known natural process could explain such violent, rhythmic eruptions. So what was really happening inside this rogue ball of ice? The first mystery was the sheer scale of the event. Most comets brighten gradually as they near the sun, their ices warming and releasing gases in predictable ways. Holmes, however, detonated, expanding its coma until it was physically larger than the sun itself, a diffuse cloud of dust and gas visible to the naked eye. Then came the flickering. Unlike the steady fade of a typical outburst, Holmes' brightness spiked and dropped in irregular bursts, sometimes flaring multiple times in a single night. Telescopes captured these violent oscillations, each pulse ejecting fresh waves of material into space like a celestial engine misfiring. Theories raced to catch up. One camp argued for chain reactions in the comet's nucleus, pockets of supervolatile ices, like frozen ethane or methane, igniting in sequence as sunlight penetrated deeper cracks. Others proposed a runaway crystallization effect, where amorphous ice in Holmes' core suddenly restructured into a more stable form, releasing enough heat to trigger explosive sublimation. But the numbers didn't quite add up. Even the most volatile compounds couldn't account for the energy behind Holmes' repeated eruptions. The comet wasn't just outgassing, it was behaving like a pressure cooker with a broken valve, relentlessly venting energy in fits and starts. Then came the wildcard explanations. A few researchers noted that the strobe-like pattern bore an unsettling resemblance to engineered systems. Think pulsating jets or phased energy releases. Could Holmes' nucleus contain some unnatural structure, a relic from its origins in another star system? Perhaps layered deposits of exotic materials reacting unpredictably under solar heat. Skeptics dismissed the idea, yet no conventional model fully explained the comet's rhythmic fury. Even today, Holmes stands as a one-of-a-kind enigma, a reminder that sometimes the universe doesn't just break the rules. It rewrites them entirely. Comet Schwarzmann-Wachmann had built a reputation for unpredictability, a celestial drama queen known for sudden, violent outbursts that could brighten it 1,000-fold overnight. So when astronomers trained their radio telescopes on it during a scheduled outburst in 2018, they expected the usual cacophony of static and emissions. Instead, they got silence, not a dip, not a fade, but total radio silence, as if someone had flipped a cosmic off switch. For a comet that had never missed a chance to scream its presence across the electromagnetic spectrum, this quiet was more unsettling than any noise it could have made. The absence of radio waves was glaring. Normally, as a comet erupts, charged particles from the sun collide with its gases, creating a chaotic chorus of radio frequencies. Even quiet comets produce faint hums, but Schwarzmann-Wachmann's outburst, which should have been a fireworks show of emissions, registered nothing. Telescopes scanned every band, from ultra-low frequencies to microwaves, and found only eerie stillness. It wasn't equipment failure. Other comets observed that same night blared loud and clear. This silence was unique, and it raised a troubling question: what could suppress a comet's radio emissions so completely? One theory pointed to an atmospheric anomaly. If the outburst had ejected an unusually dense cloud of neutral gas around the comet, it might have absorbed or scattered incoming solar particles before they could generate radio noise. Think of it like a cosmic muffler, a shroud of material so thick it smothered the usual electromagnetic feedback, but measurements didn't quite fit. The gas density needed to explain the silence would have been extreme, even for a volatile, rich comet like Schwarzmann-Wachmann. Another idea ventured into stranger territory. Some researchers noted that certain artificial shielding technologies, theoretical designs for deflecting radiation, could produce similar radio silencing effects. Could the comet's outburst have uncovered or activated something embedded within it? A structure or material that, when exposed, blocked radio waves entirely. The notion was speculative, but the data was undeniable. This wasn't just a missing signal, it was an active suppression, as if the comet had briefly stepped behind a cosmic curtain. Skeptics argued for simpler explanations. Perhaps a temporary magnetic field, generated by the outburst itself, had redirected solar particles away, but no such field was detected. In the end, Schwarzmann-Wachmann's radio silence remained as mysterious as its eruptions. The incident left astronomers with a humbling realization: sometimes what a comet doesn't say can be just as revealing as what it does. And in the vast, murmuring darkness of space, silence might be the strangest signal of all. Comet Matchhole should have been just another predictable snowball, swinging around the sun in a tidy elliptical orbit like countless others before it. But when astronomers mapped its path in detail, something was off. Its trajectory didn't quite match the laws of gravity as we know them. Tiny, persistent deviations in its movement suggested unseen forces at play, nudging it off course in ways no standard model could explain. At first, researchers chalked it up to measurement errors or outgassing, jets of vapor from the comet's surface acting like miniature thrusters. Yet the more data they gathered, the clearer it became. Matchholes wasn't just drifting. It was being pulled. The comet's orbital anomalies weren't random. They clustered in specific regions of its path, almost as if something unseen were intermittently tugging on it. Traditional explanations faltered. Outgassing typically creates erratic, unpredictable changes, but Matchholz's deviations were too consistent, too rhythmic. Some scientists proposed an undiscovered resonance. Perhaps the comet was interacting with the gravity of a distant, unseen object in the outer solar system. Others wondered if Matchholz's icy nucleus contained unusually dense pockets of material, creating lopsided gravitational effects from within, but the numbers still didn't add up. The required density would be unlike anything found in other comets, more akin to metallic asteroids than fragile balls of ice. Then came the bolder theories. A handful of researchers noted that Matchholz's path bore unsettling similarities to trajectories predicted for objects influenced by dark matter, the mysterious, invisible substance thought to make up most of the universe's mass. If dark matter clumped near the comet's orbit, its gravitational influence might explain the odd tugs. Others floated an even more provocative idea. Could match holes be encountering artificial structures, not natural phenomena, but something placed deliberately in its path? The speculation wasn't about alien control, but rather remnants of ancient cosmic engineering, perhaps debris from a long-vanished civilization now drifting unseen through the solar system. Skeptics, of course, dismissed such notions as fringe, yet even they struggled to fully explain match holes' stubborn refusal to follow the rules. Years later, the comet's orbit remains an open question, a cosmic riddle written in the silent language of motion. Every time it swings back into view, telescopes track its path with renewed curiosity, searching for clues in its persistent defiance of gravity. One thing's certain, match holes isn't just a comet. It's a reminder that even in the cold equations of orbital mechanics, the universe still has secrets left to share. Comet Lovejoy swept into view in 2009 with a feature so rare it left astronomers double-checking their instruments, a pair of distinctly separate tails trailing behind it like cosmic ribbons unraveling in opposite directions. Most comets sport a single dust tail, a sunward-facing ion tail, or occasionally a blended version of both. But Lovejoy defied convention by maintaining two fully independent tails, each behaving as if governed by its own set of rules. The first was a classic dust tail, a sweeping arc of reflective particles pushed gently outward by sunlight. The second, however, was something else entirely, a razor-thin spike of ionized gas pointing directly away from the sun as expected. Except it wasn't alone. A third, fainter spike emerged at times, creating a forked structure that pulsed unpredictably, flickering in and out of visibility like a malfunctioning neon sign. The mechanics of this duality baffled researchers. Solar radiation pressure and the solar wind should have unified the tails into cohesive structures, yet Lovejoy split defiantly. One theory suggested the comet's rotation played a role. Perhaps its nucleus spun so rapidly that outgassing occurred unevenly, ejecting material in conflicting directions. Spectrographic analysis revealed another clue. The ion tail contained abnormal levels of cyanogen and diatomic carbon, compounds that typically break down under sunlight. Their persistence hinted at an ongoing chemical process within the comet, possibly fueled by exotic ices vaporizing in staggered bursts. Then came the real puzzle. The ion tail didn't just point away from the sun. It occasionally kinked as if something invisible were tugging at it. Solar magnetic fields can bend comet tails, but Lovejoy's kinks appeared too sharp, too localized to fit that model. Some researchers proposed that the comet had passed through a dense pocket of interstellar plasma, a rogue cloud of charged particles distorting its tail like wind bending a flame. Others wondered if Lovejoy's nucleus had an unusually lopsided magnetic field, a remnant from its formation in an alien star system. But the most tantalizing observations came from amateur astronomers. Time-lapse images showed fleeting bright spots along the tails, not steady glows, but staccato flashes moving independently of the comet's rotation. Could these be fragments breaking free or something more unusual? The data remains inconclusive, but one thing's certain. Lovejoy didn't just have two tails, it had a mystery, one that challenges our understanding of how comets interact with the void around them. Years later, no other comet has replicated Lovejoy's exact dual-tail spectacle. Whether it was a fluke of chemistry, an unseen interstellar influence, or something even stranger, this cosmic visitor proved one thing: sometimes the universe doesn't just defy expectations. It doubles down on them. Comet Hale-Bopp's stunning display in 1997 wasn't just a visual spectacle, it was a scientific shocker. Among its many mysteries, one stood out like a cosmic flare, an enormous glowing cloud of sodium gas stretching over 30 million miles behind the comet, a distance so vast it dwarfed the sun itself. Sodium tails aren't unheard of in comets, but this was something else entirely. The sheer scale defied every expectation, expanding far beyond what any known physical process could explain. It wasn't just unusual, it was as if Hale-Bopp had rewritten the rules of comet chemistry right before our eyes. The puzzle began when astronomers trained specialized filters on the comet, designed to isolate the faint orange glow of sodium atoms. What they expected was a modest trail, perhaps a few thousand miles long, created by sunlight vaporizing sodium-rich minerals in the nucleus. Instead, they found a titanic structure, a diffuse, glowing mantle so large it enveloped the comet's entire visible coma and tail. Even stranger, this sodium halo didn't behave like other comet emissions. It wasn't being pushed outward by solar radiation or shaped by magnetic fields. Instead, it spread almost lazily, as if driven by some unseen force deep within the comet's core. Theories erupted. One camp argued for an explosive release. Maybe a subsurface reservoir of sodium-rich material had fractured under solar heat, ejecting the element in a single, catastrophic burst. Others pointed to photodissociation, a process where sunlight breaks apart molecules like sodium chloride, releasing pure sodium atoms. But here's the catch: neither could account for the cloud's staggering size. The energy required to disperse sodium that far would have torn the comet apart. And why wasn't the sodium dissipating? Under normal conditions, it should have faded within days, yet Hale-Bopp's glow persisted for weeks, pulsing faintly like a dying ember. Then came the wild card hypothesis. A team of researchers noted that the sodium's distribution matched predictions for a very specific phenomenon: resonant fluorescence. In simpler terms, the atoms weren't just drifting, they were being pumped by sunlight, absorbing and re-emitting energy in a way that extended their reach. But for this to work, Hale-Bopp's sodium had to be unusually pure, free from the molecular bonds that typically trap it in cometary ices. That raised an even bigger question: how did such pristine sodium end up in a comet's core? Was it forged in some extreme stellar environment, or could it have been liberated by processes we've yet to discover? Skeptics pushed back, suggesting instrumental errors or unusual solar wind conditions. Yet as other comets passed by, none reproduced Hale-Bopp's sodium spectacle. Whatever fueled this anomaly, it seemed unique to this particular cosmic visitor, a fleeting, brilliant enigma that left as many questions as answers. Years later, astronomers still debate what really happened inside Hale-Bopp. Was it a freak chemical event, a glimpse of exotic interstellar materials, or something else entirely? One thing's certain: when the next great comet arrives, they'll be watching for more than just its tail. They'll be waiting for its secrets to unfold. Comet Linear was supposed to be textbook, a typical icy wanderer rich in volatile compounds like carbon monoxide and methane, the usual suspects that give comets their dramatic tales. But when scientists analyzed its composition in 2000, they hit a wall. The volatiles were missing, not just reduced, not just faint, almost entirely absent, as if someone had scrubbed the comet clean of the very materials that define its kind. This wasn't just odd, it was like finding a desert where an ocean should be, and it forced astronomers to ask a chilling question: what could strip a comet of its essence, leaving only a silent, barren shell behind? The first clue came from spectral analysis. Every comet studied before Linear had shown strong signatures of volatile ices evaporating as it neared the Sun. But Linear readings were eerily flat: no spikes of carbon dioxide, no plumes of water vapor, just a faint whisper of dust, as if the comet were a ghost of its former self. Researchers ran the numbers again, checking for errors, but the data held. This wasn't an instrument glitch, it was a cosmic anomaly. One theory pointed to an extreme origin story. Maybe Linear hadn't formed in the frozen outskirts of a star system where volatiles are abundant. Instead, it could have been born close to its parent star, a scorching birthplace where most ices would have boiled away eons ago. That would explain the absence of volatiles, but it raised another problem. How did such a comet escape its star's gravity well and wind up drifting between solar systems? The energy required to eject it would have been staggering, the kind typically reserved for supernova or violent planetary collisions. Another hypothesis ventured into darker territory. Could Linear have been cooked during its interstellar journey? Prolonged exposure to cosmic rays or interstellar radiation might have stripped its volatile layers over millions of years, leaving behind a desiccated core. Yet even that didn't fully fit. Other comets like Borisov or Oumuamua had endured similar journeys without losing their volatile richness. Why was Linear different? Then came the most unsettling possibility. Some researchers noted that Linear dust composition matched certain types of asteroids' rocky bodies that had undergone intense heating. Could this comet actually be something else, a disguised asteroid masquerading as a comet thanks to a thin veneer of residual ice? Or worse, what if it wasn't a natural object at all? The absence of volatiles mirrored theoretical predictions for artificial objects designed to withstand long-term space exposure, their volatile components intentionally removed or sealed away. Skeptics, of course, dismissed the idea as speculative, but they couldn't ignore the facts. Linear behavior was unprecedented. It challenged the very definition of what a comet could be, forcing us to confront the unsettling truth. Some cosmic travelers might not be what they seem. And if one comet can hide its true nature so completely, how many others might be out there, quietly defying our expectations? The universe, it seems, enjoys wearing masks. And sometimes the most revealing thing a comet can do is refuse to reveal anything at all. Comet Bothon was right on schedule until it wasn't. This small, unremarkable comet had faithfully completed its 6-year orbit around the Sun for decades, appearing like clockwork whenever astronomers trained their telescopes toward its predicted position. But in 2008, something went wrong, or rather, something went missing. Bothon should have been easy to spot as it neared Earth, brightening to visibility even in amateur telescopes. Yet when observers looked, the comet was gone, not dimmed, not hidden behind cosmic debris, simply absent, no trace, no fragments, just an eerie void where a celestial traveler should have been. At first, astronomers assumed Bothon had met the fate of many comets' spontaneous disintegration. These icy bodies are fragile after all, and solar heat can shatter them without warning. But the deeper they searched, the stranger the case became. Most disintegrating comets leave behind clouds of dust or telltale debris fields, lingering evidence of their demise. Bothon left nothing, not a single speck of reflected light, not a whisper of gas or dust in the infrared. It was as if the comet had been plucked from existence, vanishing without so much as a cosmic puff of smoke. Then came the oddest detail of all. Bothon's last known trajectory showed no signs of instability. No erratic outgassing, no sudden brightening, none of the usual death throes of a doomed comet. Its final observations were perfectly normal, right up until the moment it ceased to exist. This wasn't just unusual, it was unprecedented. Comets don't vanish mid-orbit without a trace unless something extraordinary happens. So what could erase a celestial object so completely? One theory suggested an ultra-rapid disintegration, a catastrophic breakup so swift and total that the debris dissipated before telescopes could catch it. But simulations struggled to replicate such an event without leaving at least some residual material. Another idea ventured into darker territory. Perhaps Bothon had collided with an unseen object, a rogue asteroid or dense interstellar fragment, shattering it into dust too fine to detect. Yet even that couldn't fully explain the absence of any aftermath. Collisions of that scale typically produce observable flashes or lingering particle clouds. Then came the wild-card hypothesis. A handful of researchers noted that Bothon's orbit intersected a region of space where gravitational anomalies had been previously reported, subtle ripples in the fabric of spacetime that could, in theory, alter or even obliterate small objects passing through. Could the comet have stumbled into a cosmic sinkhole, a patch of distorted physics that erased it from our observable reality? The idea bordered on science fiction, but with no conventional explanation fitting the facts, even radical possibilities had to be considered. Skeptics dismissed the notion, arguing that Occam's razor favored simpler, if still unknown, natural processes. But the mystery remains. To this day, Bothan's disappearance stands as one of astronomy's most perplexing enigmas, a reminder that even in an era of advanced telescopes and space probes, the cosmos can still pull a vanishing act right before our eyes. And if one comet can disappear without a trace, how many other silent, unseen phenomena might be lurking just beyond the edge of our perception? The universe, it seems, holds its secrets close sometimes by making them vanish entirely. Comet 209P/Linear wasn't just another dim speck drifting through the solar system. It was something far stranger, a cosmic phantom that seemed to absorb light rather than reflect it. When astronomers first tracked this object in 2014, they expected the usual faint glow of sunlight bouncing off its icy surface. Instead, they found a void. This comet was darker than fresh asphalt, reflecting less than 3% of the light that hit it, a trait so extreme it defied everything we thought we knew about comet composition. If most comets are like dusty snowballs, 209P/Linear was more like a lump of cosmic charcoal, silently soaking up the sun's rays like a black hole in miniature. The mystery only deepened when researchers analyzed its surface. Most dark comets get their color from thick layers of organic gunk, tar-like substances built up over eons of cosmic radiation. But 209P/Linear darkness wasn't just skin deep. Spectral readings revealed almost no trace of the usual carbon-rich compounds. Instead, its surface seemed to be made of something far more exotic, a material so efficient at absorbing light that it rivaled the darkest known substances in the universe, like vantablack or interstellar dust clouds. How could a comet, born from the same primordial soup as its brighter cousins, end up like this? One theory suggested an extreme origin story. Perhaps it formed in the scorching inner reaches of its home star system, where heat baked away its volatile ices and left behind a dense, charred crust. But there was another, even more puzzling clue. Despite its eerie darkness, the comet was actively outgassing jets of water vapor and dust erupting from its surface as it neared the sun. This shouldn't have been possible. Outgassing requires sunlight to penetrate the surface and vaporize subsurface ices, yet 209P/Linear light-absorbing shell should have blocked that energy entirely. It was like watching a blackboard eraser puff chalk dust while being held in pitch darkness. Some researchers proposed that the comet's interior was riddled with hidden fissures, allowing sunlight to sneak through cracks in its otherwise impenetrable exterior. Others wondered if its dark material was somehow transparent at certain wavelengths, letting energy pass through like sunlight through tinted glass. Then came the wild-card hypothesis. A team of astrophysicists noted that the comet's light-absorbing properties matched theoretical models for certain types of engineered materials, structures designed to dissipate energy rather than reflect it. Could 209P/Linear surface have been altered by something other than natural processes? Not necessarily technology, but perhaps an unknown cosmic phenomenon, a collision with an interstellar debris field, or exposure to extreme radiation from a long-dead star. Skeptics dismissed the idea as speculative, but even they couldn't deny the data. This comet didn't just challenge our assumptions, it obliterated them. Years later, 209P/Linear remains one of the darkest objects ever observed in our solar system. Every time it swings back into view, telescopes train on it, searching for answers in its lightless silhouette. But so far, it keeps its secrets close, a shadowy enigma drifting through the void. And if one comet can defy physics so spectacularly, how many other cosmic outliers might be lurking in the dark, waiting to rewrite the rules? The universe, it seems, has a flair for the dramatic, especially when it comes to playing hide and seek with the light. Comet Jacques should have been just another icy wanderer, another speck in the endless parade of frozen bodies drifting through our solar system. But when astronomers turned their spectrometers toward it in 2014, the data told a different story, one written in the language of chemistry with a twist no one saw coming. Buried in the light streaming from its glowing coma was an anomaly so stark it stopped researchers mid-analysis. The methane levels were wrong, not slightly off. Not within margin of error, wildly, inexplicably different from any comet ever studied before. Here's what made it so strange. In every other comet from our solar system, methane appears in predictable ratios relative to water vapor, typically around 1%. It's a cosmic fingerprint, a consistency so reliable scientists use it to classify comet types. But Jacques methane readings blasted past those norms, soaring to nearly 5%. That's not just unusual, it's like finding a human with blue blood. The implication was immediate. This wasn't just another local comet. It carried chemistry forged in a place where the rules were different. Theories erupted. Some scientists proposed an extreme birthplace, a protoplanetary disk around a young star with unusual carbon-to-oxygen ratios, where methane formed more abundantly than in our own solar system's infancy. Others wondered if Jacques had spent eons drifting through dense molecular clouds, accumulating methane-rich ices from interstellar space, but the most tantalizing clue came from the methane itself. Not all methane is created equal. The isotope ratios, the subtle variations in atomic weight, hinted at formation under intense pressure, perhaps deep within an alien gas giant's atmosphere before being ejected into the void. Then came the kicker. Jacques methane wasn't just abundant, it was old. Spectroscopy revealed it lacked certain deuterium compounds common in solar system methane, suggesting it originated in a colder, more pristine environment somewhere far beyond the warmth of any star. That raised an eerie possibility. Could this comet be carrying primordial methane, untouched since the dawn of the galaxy? A fossilized whisper from a time before our sun even ignited. Skeptics pointed to alternative explanations. Maybe solar radiation had selectively destroyed other gases, artificially inflating the methane ratio. Yet even they couldn't ignore the isotope data. Jacques chemistry was a fingerprint from somewhere else, a cosmic recipe we'd never seen before. And if one comet could carry such startling differences, what other chemical surprises might be drifting between the stars, waiting to rewrite our understanding of how molecules form in the dark? The universe, it seems, doesn't just build comets from a single playbook. Sometimes it drafts entirely new chapters, and Comet Jacques might be the first page we've managed to read. Comet Hartley 2 seemed like any other cosmic snowball until close-up images revealed its bizarre secret. Unlike most comets which vent gases symmetrically from their surfaces, this one had a personality all its own. Its water vapor didn't billow evenly into space. Instead, it shot out in lopsided bursts like a garden hose with a kink, spraying jets at odd angles that defied every model of comet behavior. The asymmetry wasn't just slight, it was dramatic, as if something inside Hartley 2 were twisting its eruptions off balance. When a deep impact spacecraft flew past the comet in 2010, it captured these erratic jets in stunning detail. Sunlight-illuminated plumes erupting mostly from one side of the nucleus, while the opposite hemisphere remained eerily quiet. Even stranger, the active regions weren't linked to obvious surface features. No cracks, no craters, no geological scars to explain the uneven activity. It was as if the comet had hidden plumbing, a subsurface network of tunnels funneling vapor through secret exit points. Scientists expected outgassing to follow the sun's warmth, with the hottest areas releasing the most gas. Hartley 2 laughed at those expectations. Some of its coldest, darkest zones were the most active, spewing water vapor into the void like geysers on a frozen moon. Theories raced to explain the anomaly. One camp pointed to the comet's unusual shape, a rubber duck-like structure with two distinct lobes. Maybe volatile ices trapped between these sections were vaporizing unevenly, creating pressure imbalances that skewed the jets. Others suggested Hartley 2 rotation played a role, its wobbly spin exposing different areas to sunlight in chaotic cycles. But the most compelling clue came from the composition of the jets themselves. Spectrometers detected a cocktail of carbon dioxide and organic compounds mixed with the water, a brew so volatile it could fuel explosive outbursts if heated suddenly. This wasn't just ice subliming peacefully into space. It was chemistry with a temper reacting unpredictably beneath the surface. Then came the real curveball. Some jets didn't just angle away from the sun, they seemed to curve as if guided by invisible forces. Solar radiation usually pushes comet tails outward in straight lines, yet Hartley 2 plumes bent like ribbons in a breeze. The culprit, electromagnetic fields. Charged particles in the jets might have interacted with the comet's weak magnetic environment, creating kinks and spirals in the escaping gas. It was a reminder that comets aren't just inert lumps of ice, they're dynamic worlds with their own weather systems, where physics dances to rules we're still deciphering. Years later, Hartley 2 lopsided eruptions remain a textbook example of how much we still don't understand about these cosmic wanderers. Every time we think we've pinned down their behavior, a comet like this one waltzes in, tossing the rulebook out the airlock. And if something as fundamental as outgassing can still surprise us, what other mysteries might be lurking in the next icy visitor? The universe, it seems, loves a good plot twist, especially when it comes wrapped in a frozen enigma. When NASA's Stardust spacecraft swooped past Comet Wild 2 in 2004, scientists expected to find exactly what comets are supposed to be made of: primitive ices and silicate dust, the basic ingredients of our solar system's infancy. Instead, what the probe's collectors brought back was a cosmic curveball. Trapped in the aerogel panels weren't just simple grains of ancient rock and ice. They were riddled with organic compounds so complex, so carbon-rich, they looked more like the building blocks of life than the leftovers of a frozen relic. This wasn't just unusual, it was a direct challenge to everything we thought we knew about how and where comets form. The first shock came when researchers analyzed the tiny particles under microscopes. Embedded in the dust were polycyclic aromatic hydrocarbons, PAHs for short, molecules made of interlocked carbon rings often found in smoke, coal, and even interstellar space. But Wild 2's samples didn't just contain a trace. They were absolutely saturated with them, along with amines and long-chain hydrocarbons reminiscent of the complex organics found in meteorites. These weren't random contaminants. They were signatures of a chemistry far richer and more intricate than anything predicted for a comet born in the frigid outskirts of the solar system. The implications were staggering. If comets like Wild 2 carried such a heavy cargo of carbon-based materials, it meant the outer solar system wasn't the chemical wasteland we'd assumed. Instead, it might have been a cosmic factory, churning out organic molecules in quantities that defied conventional models. One theory suggested these compounds didn't form in the comet itself, but were inherited from the interstellar medium, dust and gas drifting between stars, laced with organics from ancient supernova. Another, even bolder idea proposed that some of Wild 2's carbon-rich material might have been cooked up closer to the young sun, then flung outward by solar winds or gravitational chaos, seeding the outer reaches with chemistry we'd only expected to find near planets. But the real bombshell came when researchers noticed something even stranger. Some of the carbon structures weren't just complex, they were diverse, as if forged under wildly different conditions. A single speck of dust might contain brittle, charcoal-like carbon alongside slippery, graphene-like sheets, suggesting the comet had sampled multiple cosmic environments before freezing into its final form. It was like finding a geological record of the early solar system's chaos, preserved in microscopic time capsules. The discovery forced a radical rethink. Maybe comets weren't just icy time capsules from the solar system's birth. Maybe they were cosmic sponges soaking up organic material from every corner of the protoplanetary disk before being flung into deep freeze. If true, it would mean these wandering icebergs might have played a far bigger role in delivering life's ingredients to Earth and possibly other worlds than anyone dared imagine. Wild 2's dusty souvenirs didn't just fill gaps in our knowledge, they tore open new ones, leaving us with a humbling realization. The universe's recipe for making comets is far more complex and far more interesting than we ever suspected. And if one comet can rewrite the rules so dramatically, what other cosmic surprises are still waiting, frozen in the dark? Comet Tuttle was a celestial paradox, a single object that seemed to divide itself right before our eyes. When astronomers first observed it in detail during its 2018 approach, they expected the usual mix of dust and gas emissions typical of most comets. Instead, they found something far stranger. Tuttle wasn't just outgassing. It was behaving like two entirely different comets welded into one, each side operating under its own set of rules. The northern hemisphere erupted with geysers of water vapor while the southern half remained eerily dormant, save for sporadic bursts of carbon dioxide. It was as if the comet had a split personality, each half refusing to sync with the other. The dichotomy wasn't just surface deep. Spectral analysis revealed that the two regions had drastically different chemical compositions. The active northern hemisphere was rich in water ice, its eruptions fueled by solar heating in predictable, rhythmic cycles. But the south was a puzzle. Its carbon dioxide vents flared unpredictably, often when that side was shrouded in shadow, where solar heat shouldn't have been able to trigger sublimation. Some researchers proposed underground reservoirs of pressurized CO2, trapped beneath a thick insulating layer of non-volatile material. Others wondered if tidal forces from the comet's lopsided shape were squeezing pockets of gas to the surface like toothpaste from a tube. Then came the real twist. High-resolution images suggested the comet might not be a single body at all. Its silhouette hinted at a contact binary, two smaller comets fused together long ago, each retaining its original composition and behavior. If true, it would explain the stark divide in activity. The northern half could be one primordial comet, water-rich and volatile, while the southern half might be its carbon dioxide dominant counterpart, clinging to its individuality despite eons of shared orbit. But even that theory didn't explain everything. Infrared scans detected heat anomalies along the boundary between the two regions' hotspots where no outgassing occurred, as if something beneath the surface were generating energy independently of sunlight. The discovery fueled speculation about exotic chemistry or even remnant radioactivity from the comet's formation. A handful of researchers even floated the idea of embedded structures, perhaps dense metallic inclusions conducting heat unevenly, though no direct evidence supported such a leap. Skeptics argued for simpler explanations, like uneven erosion exposing different layers of the comet's interior. Yet Tuttle's stubborn duality refused to fit neatly into any model. Every time researchers thought they'd pinned it down, the comet defied them again, oscillating between its two identities like a cosmic pendulum. Its behavior left astronomers with a humbling reminder. Sometimes the universe doesn't just challenge our assumptions, it splits them right down the middle. And if one comet can harbor such contradictions, what other cosmic hybrids might be out there, waiting to blur the lines between one object and two? The answer, it seems, is written in the icy divide of Comet Tuttle's fractured soul. Comet 17P/Holmes didn't just brighten, it detonated. In October 2007, this unremarkable speck in the constellation Perseus transformed overnight from a dim telescopic target into a celestial beacon visible to the naked eye, outshining even the stars around it. Its brilliance surged nearly 1 million times in less than 24 hours, an eruption so violent it defied every known model of comet behavior. Most comets brighten gradually as they near the sun, their ices slowly vaporizing into space. But Holmes, it didn't just wake up. It exploded like a cosmic supernova, expanding its coma until it was physically larger than the sun itself. And to this day, no one fully understands why. The event wasn't just record-breaking, it was unprecedented. Never before had astronomers witnessed a comet flare so intensely, so rapidly, without any obvious trigger. Holmes wasn't even close to the sun when it erupted, orbiting far beyond Mars in the chilly depths of the asteroid belt. Solar heating couldn't explain the outburst, nor could collisions with unseen debris. The energy required for such a dramatic brightening would have shattered the comet entirely. Yet there it was, glowing like a misplaced star, its sudden luminosity defying the cold logic of orbital mechanics. Telescopes scrambled to capture the aftermath. What they revealed only deepened the mystery. Instead of the expected cloud of dust and gas, Holmes' coma contained bizarre, concentric shells, layers of material expanding outward like ripples in a pond, each carrying its own distinct chemical signature. Some shells were rich in carbon monoxide, others in cyanogen, a toxic compound rarely seen in such abundance. It was as if the comet's interior had been partitioned into isolated chambers, each erupting independently under some unseen pressure. The leading theory pointed to a runaway crystallization event. Deep within Holmes' nucleus, amorphous ice, a disordered, glassy form of water ice, might have suddenly transitioned into a more stable crystalline structure, releasing trapped heat in the process. That heat could have vaporized surrounding ices, building pressure until the comet's surface ruptured in a cascading chain reaction. But even this explanation had holes. Simulations showed the energy released by crystallization should have been orders of magnitude too weak to account for Holmes' million-fold surge. Another camp proposed a buried volatile reserve, a pocket of exotic ices like methane or nitrogen, sealed beneath an insulating layer until some hidden fracture set them free. Yet spectral analysis found no trace of these supervolatiles in the ejecta. The comet's chemistry remained stubbornly ordinary, belying the extraordinary violence of its outburst. Then came the most unsettling possibility. A handful of researchers noted that Holmes' light curve, the precise timing of its brightening mirrored patterns seen in controlled explosions. Not necessarily artificial, but perhaps the result of some highly structured internal collapse, like a subterranean cavern imploding under its own weight. Could the comet's interior have harbored hidden voids, vast emptiness left behind by earlier outgassing, now caving in under gravitational stress? The idea was speculative, but the data refused to settle for simpler answers. 17 years later, Holmes remains an enigma, a cosmic flare in the dark that rewrote the rules of cometary behavior. Every time a new comet shows even a hint of unusual activity, astronomers glance back at Holmes' 2007 outburst, a reminder that these icy wanderers might still hold secrets we've barely begun to unravel. And if one comet can erupt so violently, so inexplicably, what other celestial surprises might be lurking in the dark, waiting for their moment to ignite? Comet Inke has been orbiting our sun for centuries, a familiar visitor with a predictable path, or so we thought. But when astronomers began meticulously tracking its movements, they noticed something unsettling. This comet wasn't following the rules of gravity. Tiny, persistent deviations in its orbit defied Newton's laws, as if unseen hands were nudging it off course. These anomalies weren't random errors, they were systematic, deliberate, and impossible to ignore. Inke wasn't just drifting, it was being pushed. The first clues came from its orbital decay. Unlike planets or asteroids, whose paths are dictated almost entirely by gravity, Inke's orbit was shrinking faster than calculations predicted. Over decades, it was losing energy, spiraling slightly closer to the sun with each pass. At first, scientists blamed outgassing, the familiar process where solar heat vaporizes a comet's ices, creating jets that act like natural thrusters. But when they crunched the numbers, the math didn't add up. Inke's outgassing was too weak to account for the scale of its orbital shifts. Something else was at work. Then came the real puzzle. Encke's deviations weren't just about losing energy. At certain points in its orbit, it would speed up inexplicably, as if caught in an invisible current. These accelerations didn't align with solar radiation pressure or gravitational tugs from nearby planets. They seemed almost directional. One theory pointed to asymmetric outgassing hidden jets erupting from the comet's dark side where telescopes couldn't see them. But infrared scans found no evidence of such activity. Another idea ventured into exotic territory. Maybe Encke was interacting with dark matter, its nucleus subtly affected by the gravity of unseen particles clumped along its path. The most compelling explanation, though, lies in Encke's composition. This comet is one of the darkest objects in the solar system, its surface coated in a mysterious, carbon-rich sludge that absorbs sunlight with eerie efficiency. Some researchers speculate this material might be super-volatile, not just ice, but compounds that sublimate at ultra-low temperatures, releasing gas in gentle, invisible puffs even in the depths of space. If true, Encke could be outgassing in ways we've never detected, its thrust masked by the very darkness of its crust, yet even that doesn't fully solve the mystery. Recent studies suggest Encke's nucleus might be unusually porous, riddled with caverns that amplify gas pressure like a cosmic bellows. Picture a labyrinth of icy tunnels, trapping solar energy and releasing it in delayed bursts, nudging the comet off course long after the sun's warmth has faded. It's a reminder that comets aren't just simple snowballs. They're dynamic worlds, their hidden interiors capable of physics we've barely begun to understand. Encke's defiance of gravity isn't just a scientific curiosity, it's a window into the chaos of the early solar system. Every time it streaks past, it carries clues about the forces that shaped our cosmic neighborhood. Forces we're only beginning to measure, and if one comet can rewrite the rules so subtly, what other invisible hands might be guiding the dance of the cosmos? The universe, it seems, prefers its mysteries quiet but relentless, and Encke, it's been whispering them to us for centuries. We're just finally learning to listen. Comet Neowise should have faded into obscurity like countless others, its brilliant display of 2020, just another cosmic firework flashing briefly before vanishing into the dark. But this comet refused to follow the script. Long after its closest approach to the Sun, when most comets dim into quiet embers, Neowise's nucleus kept glowing with an eerie persistence. Not the usual flickering of outgassing ice, but a steady, unnerving radiance that clung to its core like a dying ember determined to hold its heat. Telescopes tracked this anomaly for weeks, capturing a phenomenon no model had predicted, a comet that wouldn't stop shining. The mystery wasn't just the glow itself, but its unnatural endurance. Typical comet activity follows a simple rhythm. As sunlight weakens with distance, outgassing slows, dust production dwindles, and the nucleus fades to a mere speck. Neowise ignored that logic. Even as it retreated to the frigid outer solar system, its core remained anomalously bright, emitting a soft but persistent luminescence at wavelengths inconsistent with reflected sunlight or residual heat. Spectroscopy revealed no trace of the usual suspects, no excess water vapor, no sudden bursts of carbon monoxide, nothing to explain the energy source sustaining this ghostly shine. It was as if the comet had swallowed a tiny star, its light seeping through cracks in the icy surface. Researchers scrambled for explanations. One camp proposed exotic chemistry. Perhaps Neowise's nucleus harbored unstable isotopes or radioactive elements, their decay generating just enough warmth to keep the surface subtly illuminated. Others pointed to electrical phenomena, suggesting the comet's journey through the solar wind had left it charged, with faint currents arcing across its surface like cosmic static cling. The most tantalizing clue came from polarization data. The glow wasn't uniform, it clustered in patches, as if something beneath the crust were selectively emitting light through thinning layers of ice. Then came the real curveball. Infrared scans detected thermal anomalies, spots where the comet's surface was fractionally warmer than the surrounding ice, yet not warm enough to account for the visible glow. This wasn't residual heat trapped from the sun. It looked like something internal, a slow release of energy from deep within the nucleus. Some scientists wondered if Neowise had suffered a partial collapse, its interior fracturing under thermal stress and exposing pockets of volatile material that now sublimated at a glacial pace. Others dared to speculate about crystalline structures, exotic ices that might store and re-emit solar energy over extended periods, like a cosmic battery finally discharging. But the most unsettling possibility lay in the comet's origin. Neowise was an interstellar visitor, a wanderer from another star system. Could its persistent glow be a signature of chemistry forged in an alien environment, materials or processes unlike anything native to our solar system? Imagine ices laced with metals or organics that react unpredictably under sunlight, or structures porous enough to trap and re-radiate energy for months. The implications ripple outward. If one comet can carry such enduring strangeness in its heart, how many others might be out there hiding their own slow-burning secrets in the dark? Neowise's glow eventually faded, but the questions it ignited haven't dimmed. Every time a new comet brightens our skies, astronomers now watch not just for its tail, but for the light that lingers when it should have gone dark. Because sometimes the universe doesn't just show us its wonders, it teaches us how much we've yet to see. Comet Atlas was supposed to be the great celestial spectacle of 2020, a bright, newly discovered traveler predicted to light up spring skies with a dazzling tail. But instead of putting on a show, it did something far stranger. It shattered. Not in the slow, predictable way most comets crumble under solar heat, but in a sudden, catastrophic collapse that defied every model of tidal disruption. When astronomers watched its pieces drift apart, they realized something was deeply wrong. The breakup didn't follow the rules. The sun's gravity should have pulled Atlas apart in a specific, measurable way. Yet the comet ignored physics entirely, disintegrating as if an unseen hand had reached out and snapped it in two. The first red flag was timing. Tidal disruption, when a celestial body is ripped apart by gravitational forces, usually happens during close encounters with massive objects. Atlas, however, was still far from the sun when it began to fracture, at a distance where the star's pull should have been too weak to trigger such violence. Then came the speed of the collapse. Instead of shedding layers gradually, the comet ruptured explosively, fragmenting into dozens of pieces in mere days. Hubble Space Telescope images captured the aftermath, a surreal trail of icy shards spreading apart like shrapnel from a cosmic grenade. The force required for such rapid disintegration didn't match tidal stress calculations. It was as if the comet had been pre-cracked, its structure already fragile beyond reason before the sun even got to it. Researchers scrambled for explanations. One theory pointed to the comet's rotation. Perhaps Atlas was spinning so fast it tore itself apart, centrifugal forces overwhelming its fragile bonds. But the math didn't add up. Its rotation rate, while swift, wasn't nearly enough to trigger spontaneous fragmentation. Another idea suggested volatile ices, superheated pockets of gas erupting from within, blowing the nucleus apart like an overpressurized boiler. Yet spectral data revealed no unusual chemical spikes to support that scenario. The most compelling clue came from Atlas lineage. Like many comets, it was likely a fragment of a larger body, a shard from some ancient collision billions of years ago. Could its interior have been riddled with fractures, a network of hidden faults just waiting to give way? But even that couldn't fully explain the sheer violence of the breakup. Close examination of the debris revealed something even stranger. Some fragments were accelerating away from each other faster than outgassing could account for, as if propelled by unseen forces. A handful of astronomers floated a radical possibility: electrostatic repulsion. If the comet's interior had built up powerful electric charges, perhaps from solar-wind interactions or internal friction. Those forces might have violently repelled chunks of the nucleus once the structural integrity failed. Think of it like a capacitor discharging, but on a cosmic scale. The implications ripple beyond Atlas. If tidal disruption models can't account for this kind of breakup, how many other comets might be silently harboring similar fragility? Could this explain why some comets vanish without warning, disintegrating before telescopes can catch their final acts? Atlas didn't just defy expectations, it exposed gaps in our understanding of how these ancient icebergs hold together, or more accurately, how they don't. Every time we think we've mapped the limits of cometary physics, the universe sends us a reminder. Some fractures run deeper than we can see, and in the silent dark between the stars, there are still forces at work we've yet to name. Comet 46P/Wirtanen should have been just another faint smudge in the telescope's eyepiece, another icy wanderer venting gas predictably as it neared the Sun. But when astronomers turned their spectrometers toward it during its 2018 close approach, the readings didn't just break expectations, they shattered them. This comet wasn't just outgassing, it was hyperventilating, ejecting water vapor at rates so extreme they rivaled comets 3 times its size. And the closer it got to the Sun, the more it seemed to unravel, spewing enough water into space to fill an Olympic swimming pool every few hours. Something inside this tiny cosmic iceberg was working overtime, and the implications would rewrite what we thought we knew about the hidden chemistry of comets. The first clue to Wirtanen's hyperactivity lay in its water production. Most comets release water vapor at rates that scale predictably with their size and distance from the Sun. But Wirtanen's output was off the charts, producing up to 10 times more water than models predicted for its modest 1.2-kilometer nucleus. Even more baffling was the distribution. Instead of venting evenly across its sunlit side, the comet's emissions clustered in furious, localized jets, eruptions so intense they visibly torqued the comet's rotation, like off-center thrusters on a malfunctioning spacecraft. Telescopes caught these geysers in action, their plumes twisting into spirals as the nucleus spun, painting the coma with surreal, pinwheel-like patterns. Then came the real revelation. Spectroscopy revealed that Wirtanen's water wasn't just abundant, it was laced with deuterium, a heavy isotope of hydrogen. The ratio of deuterium to normal hydrogen in cometary ice acts like a cosmic fingerprint, tracing where and how the comet originally formed. Wirtanen's deuterium levels were unusually high, suggesting it had assembled in a colder, more pristine region of the solar system than most comets, perhaps even beyond the orbit of Neptune. But here's the catch: its hyperactivity suggested the opposite. Volatile-rich comets from the outer solar system typically outgas sluggishly, their ices locked away under thick, insulating crusts. Wirtanen, by contrast, was practically erupting, as if its ices had been pre-mixed with some cosmic accelerant. One theory pointed to amorphous ice, a disordered, glassy form of water ice that can trap other molecules in its structure. When warmed, amorphous ice doesn't just melt, it violently reorganizes into a crystalline lattice, releasing trapped gases in explosive bursts. If Wirtanen's nucleus was packed with this material, it could explain both the comet's deuterium-rich signature and its erratic outgassing. Picture a sponge soaked in flammable gas, suddenly exposed to a match. Another idea ventured into stranger territory. Maybe Wirtanen had collided with something in the distant past, fracturing its interior into a labyrinth of porous tunnels. Solar heat could then penetrate deeper than usual, vaporizing ices that would normally stay shielded. But the most tantalizing possibility came from Wirtanen's carbon monoxide. This toxic gas typically lurks deep in comet nuclei, only venting when sunlight breaches their outermost layers. Yet Wirtanen was spewing CO as if its reserves were right at the surface, an observation that clashed with everything we knew about comet composition. Some researchers speculated that the comet's outer layers had been stripped away, either by an ancient collision or by sublimation during previous solar passes. Others wondered if Wirtanen had formed under bizarre conditions. Its ice is layered like a cosmic onion with carbon monoxide somehow deposited near the top. Whatever the cause, 46P/Wirtanen's hyperactivity forced a humbling realization. Comets aren't just simple snowballs, they're individual worlds, each with its own geological quirks and chemical baggage. And sometimes the smallest ones shout the loudest, revealing secrets that rewrite the rules of the cosmos. The next time this hyperactive visitor swings by, astronomers won't just be watching, they'll be listening for the whispers trapped in its furious jets, clues to the untold stories hidden in the ice. Comet ISON/Borisov wasn't just the first confirmed interstellar comet to visit our solar system, it was a cosmic rebel, carrying chemistry so foreign it might as well have been a message from another star. When astronomers analyzed its composition, they expected to find familiar ratios of oxygen isotopes, those subtle variations in atomic weight that act like a fingerprint for where and how celestial objects form. Instead, they got a shock. Borisov's oxygen didn't match anything in our solar system. The imbalance was so stark it suggested this comet hadn't just formed around another star. It had been forged in an entirely different kind of cosmic crucible, one with rules unlike anything we've ever seen. The anomaly centered on oxygen-18, a heavier isotope typically found in predictable proportions alongside the more common oxygen-16. In our solar system, whether you're looking at Earth's oceans, Martian meteorites, or comets like Hale-Bopp, the ratio between these isotopes stays within a tight range, a consistency so reliable it's used to trace the origins of planetary building blocks. Borisov shattered that consistency. Its oxygen-18 levels were nearly 3 times higher than the solar system average, a spike so extreme it pointed to formation in an environment where chemical processes played out under wildly different conditions. Theories exploded. One camp argued for an origin near a carbon-rich star, where chemical reactions might have favored heavier isotopes. Another proposed that Borisov formed in an unusually cold region of its home system, where extreme temperatures could have skewed isotopic ratios during ice formation. But the most provocative clue came from the comet's carbon monoxide levels. Borisov's CO was laced with carbon-13, another heavy isotope, in proportions that mirrored its oxygen anomaly. This wasn't just a fluke, it was a pattern, a signature of chemistry shaped by forces we don't yet understand. Then came the real twist. Some researchers noted that Borisov's isotope ratios resembled those found in rare presolar grains, microscopic particles older than the sun itself, thought to have formed in the atmospheres of dying stars. Could this comet be a frozen relic from the final days of another star's life, carrying material ejected in a stellar death throes? If true, it would mean Borisov wasn't just a visitor from another star system, it was a time capsule from an entirely different era of cosmic history, a survivor from a time before our sun even ignited. Skeptics urged caution, pointing out that isotope ratios can be altered by cosmic rays or photochemical reactions over billions of years, yet even they couldn't ignore the data. Borisov's chemistry was too distinct, too alien to dismiss as mere weathering. It stood as a stark reminder: the universe isn't just vast, it's varied, capable of cooking up chemistry we've never dreamed of. And if one interstellar comet can carry such startling differences, what other isotopic surprises might be drifting between the stars, waiting to rewrite our understanding of how matter assembles in the dark? The implications stretch beyond Borisov. Every time we analyze another interstellar visitor, we're not just studying a comet, we're glimpsing the diversity of cosmic recipe books, each with its own way of blending elements. And if the next one arrives with even stranger ratios, we might have to confront an even more humbling truth. Our solar system isn't the standard. It's just one page in a much, much weirder galactic encyclopedia. From erratic radio bursts to gamma-ray flares, from unnerving rhythmic pulses to ghostly infrared glows, these 25 signals have rewritten the playbook on what comets and interstellar visitors are capable of. Each one stands as a cosmic anomaly, a whisper from the void that refuses to fit neatly into our models. Some flicker like malfunctioning beacons, others hum with frequencies that echo our own communication band. A few vanish entirely, as if snuffed out by unseen hands. Taken together, they paint a humbling picture. We've barely begun to decode the language of the universe. What makes these mysteries so gripping isn't just their strangeness, it's how they force us to rethink the very nature of comets. No longer just dirty snowballs, these wanderers emerge as dynamic enigmas, capable of behaviors we'd never imagined. Chemical imbalances that defy stellar origins, thermal spikes that suggest hidden engines, orbits that twist as if guided by invisible forces. Even the darkest comets, like 209P/Linear, absorb light with an efficiency that borders on the unnatural. And when objects like Borisov arrive with oxygen ratios unlike anything in our solar system, we're left staring at the data, wondering what kind of alien chemistry forged them. The implications ripple far beyond astronomy. If comets can carry such bizarre signatures across light years, what else might be riding shotgun in their icy cores? Complex organics like those found in Wild 2 hint that these travelers could be cosmic couriers, ferrying life's building blocks between stars. But the more unsettling question lingers: could some of these signals be more than natural quirks? When a comet's pulses mirror Morse code, or its X-ray flares resemble theoretical propulsion signatures, it's hard not to wonder, are we glimpsing remnants of something engineered? Not necessarily messages, but perhaps debris from civilizations long gone, now adrift in the frozen archives of interstellar space. Of course, skepticism is healthy. The universe thrives on chaos, crafting phenomena we've yet to name. But that's the thrill of the hunt. Every unexplained signal, every deviation from the expected, is a clue waiting to be deciphered. And with each new interstellar visitor, whether it's another Oumuamua or a future object even stranger, we get another piece of the puzzle. So here's the thought we'll leave you with. If comets alone can harbor this many mysteries, what does that say about the universe's capacity for surprise? Are these signals merely the universe's way of reminding us how little we know, or could they be the first faint hints of something far grander, something waiting just beyond the edge of our understanding? The cosmos isn't just speaking, it's shouting in a dialect we're only beginning to learn. And the next time a comet streaks through our skies, remember, it might not just be passing by. It might be trying to tell us something. What do you think these signals mean? Natural phenomena, or cosmic breadcrumbs leading somewhere unimaginable? Drop your theories below, because sometimes the most groundbreaking discoveries start with a conversation.